And yeah, I'm very happy to introduce Dan Gohman. I was thinking about giving a little introduction. I was looking in the credits file of LLVM, what Dan actually did, and I figured out he did some minor bug fixes. That's all that was written there. But actually, he's one of the top 3 committers, what I found in history, and he already gave a couple of very interesting talks. Today, we're going to hear a talk about alias analysis, and yeah, I'm very interested and excited to hear what he is going to talk about. And I think we're going to have a very interesting format of the talk, so he will explain a little bit how he wants to make this talk a little bit more interactive. And yeah, I think thanks, Dan Gohman, for speaking, and yeah, I'm excited to hear what you're talking about.
All right, thanks, Toby. All right, so just a little clarification on this. From talking to people earlier today and yesterday, I discovered that there's a wide range of people who have different experiences, different backgrounds, and different interests. And alias analysis is a wide topic. So I'd really like it if you guys could ask questions for things that you're interested in, because that will really allow me to talk about what you're interested in and not necessarily what I think you're interested in. So with that, I'd like to get started. What is alias analysis? Of course, the big question. At its simplest, take 2 pointers. And we want to know, do we know that these 2 pointers are always pointing to different memory locations? At the same time, we also ask the question, do we always know that these 2 pointers are pointing at the same memory location? And I sort of joke that that basically means that you've missed a CSE opportunity, although that's not always what it is. But the basic question is, 2 pointers, are we pointing at the same memory location or different memory locations? Alias analysis is different, but related to dependence analysis, and sometimes there's a confusion about this, so I wanted to get this out of the way early. If we have a loop like this, we have a simple loop that's iterating through an array, and each iteration of the loop references an element, and it references the element that the previous iteration referenced. Alias analysis looks within one iteration of a loop. We're not looking across iterations of a loop, we're just looking at one iteration. So in alias analysis, it'll say, OK, we have p sub I and p sub I minus 1. Those are different memory locations within one iteration. They're next to each other, but they're not overlapping at all. So alias analysis will say, there's no alias relationship here at all. There's no alias. Dependence analysis looks across loop iterations. So in dependence analysis, we'll actually say, this array reference is directly dependent on an array reference from the previous iteration. So that's really quickly the difference between dependence analysis and alias analysis is that alias analysis looks within an iteration and dependence analysis looks across iterations. So now I'm going to launch into LLVM's alias analysis API. This is basically aliasanalysis.h in LLVM. And the basic concept that we have that ties a lot of it together is the concept of a location. When we talk about a memory location, obviously we start with its address, the LLVM value that is sort of the pointer that points to that location. The location has a size, which is a size typically in bytes, and a TBAA type-based aliasing tag that identifies what the high-level type of the memory is. And I'll be talking about that a little bit more later. So there are 3 basic high-level things that aliasanalysis.h has. And then there's a bunch of other stuff that are basically wrappers around those 3 things. So these are the 3 basic concepts that are really important to understand. There's the alias, which is the main alias query, where basically you give it a location, and you give it 2 locations, and you say, do these 2 locations overlap? Yes or no, or maybe. The second category of things is the modref category. So you have modref info is a way of describing how a particular set of memory is accessed by another particular operation. So is the memory read from, written to, or both, or neither? The third category of things we have in aliasanalysis.h is the points to constant memory analysis, which basically says, given a piece of memory, does anything else in the program ever store to this memory, or is the memory conceptually constant? That's not actually an alias analysis per se, but it's basically related. It uses a lot of the same infrastructure, so we sort of bundle it together. We use a particular language when you're doing alias analysis. When we say no alias, we really mean that we have 2 pointers that are never pointing to overlapping memory locations. And practicality, what that means is that we could take those references to those memory locations and we can reorder them. No alias is all about reordering memory locations. The next main term that we have is must alias, which says that these 2 pointers are always pointing to the same thing. And that's really important for doing redundant elimination optimizations. Then we sort of have 2 different ways of saying I don't know. We say may alias, which says I really don't know anything at all. And we have partial alias, which says These two pointers are overlapping in some way, but I can't tell you exactly how. They might not be perfectly overlapping. They might not always overlap, but they're overlapping in some way. And there's a use for that we'll talk about a little bit later when we talk about how TBAA works. So LLVM IR has a number of interesting features in it which are designed to support alias analysis in particular. The most obvious is the no alias keyword. We have two different places that we can put no alias keyword. We can put it on arguments, and we can put it on return types. No alias on arguments basically corresponds to the restrict keyword in C for arguments, which essentially says the object I'm pointing to isn't pointed to by any other pointer, in short. And no alias on a return type says the return value from this function is a pointer which is not aliased by any other pointer in the program. See, I'm waving my hands a little bit here. Other interesting features that are relevant to alias analysis in LLVM are the tail keyword, which says it's used for tail calls, but what the tail keyword actually means is that this call doesn't reference any stack memory within the calling function. And that means if you're doing the get modref info, if you want to say, does this function modify a particular range of memory, and you know that range of memory is on the stack, a call with the tail call obviously doesn't reference that memory, so that's a useful feature. No capture is another interesting argument attribute that says that the pointer value is not copied outside the function in a way that will live longer than the function. Read only and read none are more modref kinds of attributes that talk about with a function or with a call, does it read memory, does it write memory, or does it not actually do anything with memory? Get element pointer is one of the sort of interesting defining characteristics of LLVM IR. At its base, it's a very simple thing. It just takes a pointer and a bunch of other operands that represent offsets from the pointer, and it adds the offsets to the pointer. That's all it really does. But we add to it. We say the get element pointer has a magic property. The pointer you get back from get element pointer has to be used to reference the same objects that the base pointer pointed to. That means if you have, I mentioned gep. Gep is a short word for get element pointer. So if you have gep of a base pointer and an offset of 0, and then you take get element pointer of the address 0, and you add a pointer to it as an offset, we guarantee you that those will give you the exact same bit-for-bit answers. This will work. But we have this additional magic that says if you take the second form, if you take a null pointer and add an offset to it, you can't dereference that pointer. That's just extra magic that we add on top of get element pointer. And that's magic that we need in order to make the optimizer work. Int to pointer and pointer to int are also related concepts here, where you can take arbitrary integer values and convert them to pointers, and pointers convert them back to arbitrary integer values. And the key rule that we have for these is that there's no guessing involved. If you happen to know where the stack is, you happen to know where a particular alloc is going to land on the stack, you might know what the numeric value that is. You might take that numeric value as a constant and try to cast that with int to pointer and make a pointer value out of it. If you do that, you might get the same bit value of the address of your alloc. But we actually say that it's undefined behavior to do that. If you actually dereference that pointer to access that alloc, that's undefined behavior. We have to know in the optimizer for alloc, we have to be able to track down all the ways you can reference that alloc. And if you can get at that alloc from calling out a magical integer constant, then you can go behind their backs. And as optimizer writers, we can't let anyone go behind our backs. Otherwise, we'll miscompile things. So I guess you can't really see this very well, but we have essentially two different ways of doing address arithmetic in LLVM IR. We can use the get element pointer magical thing that I just talked about, or we can use pointer to int to convert a pointer to an integer value, and we explicitly add an offset to it, and then we can use int to pointer to cast it back to an integer. I'm sorry, cast it back to a pointer. These two things, again, are equivalent. You can use either one. They're both semantically correct. The gep form comes with this additional restriction that the resulting pointer has to be used to point to the same object as the base pointer, whereas in the int to pointer, pointer to int case, you don't have that restriction. So the get pointer is better for the optimizer. If you're a front-end writer, you really want to make sure that you're using get element pointers instead of int to pointer, pointer to int, because the get element pointer will let the optimizer be more aggressive. In addition to interesting features that we do have, LLVM IR is also missing several notable features that sometimes people get confused about when they don't see them. So you look at LLVM, it's got structs, it's got arrays, it's got function types, it's got void types, but there's no union type. That sort of seems like it's something that's missing because C has unions. So what we actually have in LLVM is a system where memory does not have types. Memory is just an undifferentiated blob of bytes, a sequence of bytes. And you can load and store to it from pretty much any LLVM type. And there's not really any kind of a concept of this range of memory is an int, or this range of memory is a float. We just say they're bytes, and bytes can hold various amounts of data, and they can have alignment requirements, but they don't actually have any built-in types. So we don't have type memory, we don't have unions. We don't have restrict as a general type qualifier. We translate restrict into no alias on an argument, but we can't actually translate restrict in any other context. It turns out that restrict on arguments is really the most important place to have it. Argument values, because most of our optimizations are within a function rather than being interprocedural, argument values represent the sort of boundary of how far our standard analysis can look. We can trace pointer values, we can track back the usedef of how did this pointer value get computed. But once we hit an argument, that essentially is the limit. We can't go any further. So that really is the most important part where we need a hint. And we can actually capture the meaning of C99's restrict keyword right in that context. And that gives us a pretty big benefit. But we can't handle restrict in other contexts because there are more complications there. We also don't have what I call real multidimensional array accesses. We sort of have get element pointer, but we don't have any concept of the indices in a get element pointer have to be well behaved. Get element pointer is a strictly mathematical operation that has a formula for taking the indices, computing offsets, and adding offsets to a base pointer. There's no structure that says this is a dimension, this is a rank of a higher dimensional array or anything like that. Similarly, if you have one large allocation and you conceptually have multiple variables within that allocation, we have no rule that says you can't go from one variable and sort of hop into the next variable with addressing. If they're all allocated together, we permit that any addressing can get from anywhere in the allocation to anywhere else in the allocation. So within LLVM, we have a system for alias analysis that has multiple implementations of alias analysis, because there's different ways to do this. There's different algorithms that we can use. And we actually have an infrastructure in LLVM that handles chaining multiple analyses together in order to, in theory, get the best optimal results for the analysis. So we have basic analysis, and we have type-based alias analysis, and maybe we'll have others. And the way it works is you go to the first analysis and say, OK, what can you tell me about these two pointers? And it'll either come back, and perhaps it'll say no alias, or maybe it'll say must alias. If it can say one of these two things, that's a perfectly precise answer. We can't get any better than that, so we're done. However, it may come back and say, oh, I don't know. I can't actually tell. I'm not smart enough to figure that out. So I'm going to say may alias. Or maybe I'm sorry. So if it comes back and says may alias, then what we have is a situation where we need to go to the next analysis in the chain. And maybe the next analysis can answer the question. If it can come back and say no alias or may alias, then we're done. But if it says may alias, then we keep walking down the chain.
Alias or must alias.
Ooh, I'm sorry. That's a typo. It should say no alias or must alias. You're right. So if it's no alias, we know that they don't ever alias. That's our best possible answer, right? If it says must alias, then that's as precise as we're going to get, because we know the pointers are always equal. So no or must are our best possible answers. May alias means I don't really know. You have to keep asking the next analysis in the chain. And partial alias, we know that there's potentially an overlap. And we use a partial alias analysis as sort of a stop measure. So an analysis can say, I can't tell the answer, but you shouldn't keep looking. And this actually comes up with type-based alias analysis in particular. We have a very specific use for this that I'll talk about later. So this is kind of our theory of chaining multiple analyses together. So now I'm going to talk about the individual implementations of alias analysis that we have a little bit. Basic AA, and hopefully you can read this code here. So basic AA's basic approach is, given a pointer value, try to figure out how that pointer value is computed. Try to walk up what we call the usedef graph. So if it starts out in this example, this is some LLVM IR code. If we start out with the pointer E, and we say, OK, how was E computed? OK, E was computed with a get element pointer. In get element pointer, we have the magic rule that says the pointer has to come from the base, not the offset. So we can ignore N here, and we can go straight to D and say, OK, how was D computed? So we go up to D and say, well, D was computed from a phi node. Well, a phi node can have multiple inputs. And we have to actually, in this case, walk up all the possible inputs and collect all the possible things that it might point to. So in this case, it points to a bunch of other stuff, including C. So we can line up to C. C comes from a select. The select could be pointing to B, or it could be pointing to X. We have to walk out both sides again. In this case, B is pointing is computed by a bit cast. Is A. A is from a get element pointer, and the base pointer to the get element pointer is a global variable. It's the @ syntax we use in LLVM. This is the global variable. This essentially says you're done. If you're basically A and you reach this point, Z is one of the objects that E could be pointing to, one of the base underlying identified objects, we call it. So that's, we do that. We actually have to collect a set of objects because like, the phi and the select could cause it to be pointing at multiple objects. And basically what basic AA does is it computes the set for both pointers and decides if there's any intersection at all, then they might be aliasing each other. If there's no intersection, it's no alias. So basic AA is a purely stateless analysis that doesn't remember anything. Every time you give it a pointer, it just walks up the pointers and figures out what the underlying set is and then compares the sets. It's fairly simple, but it's, for what it does, is fairly effective. In the tree right now is also this thing called SkevAA. It's an alias analysis built on top of scalar evolution. I'm just mentioning it here because it was an interesting experiment that we did that works moderately OK. But since we did it, we've actually made basic AA smarter to be able to understand get element pointers more effectively. So we don't actually use SkevAA for anything right now. Global's modref is kind of a special purpose alias analysis we have in LLVM, which works on just global variables. Then it looks at the use chains for global variables. So you can say, for a given internal global variable, obviously if it's external, we can't see all the uses of it. But if it's internal, we can actually see all the uses. We can track down, does this global variable have any escapes? Or does this global variable have any stores? Or is it just loaded from? If it's just loaded, then that global variable can be made const, and we can actually do more optimization on it. So that's the sort of special purpose alias analysis. And one other very, very special purpose alias analysis is the no AA. When we have chaining, each pass is expected to be able to chain to the next pass. So we have no AA as a special pass which terminates the chain. The last pass will ask no AA. And if you get that far, the answer is I don't know, because none of the other passes knew, so I don't know. It's a special sort of trivial alias analysis at the end. At one time in LLVM, we had an implementations of Anderson's alias analysis, the Anderson's algorithm. Anderson's is an algorithm that's very strong and very effective at computing alias sets, but it takes a lot of compile time. It actually runs a very expensive solver up front that looks at the program. It uses n-cubed time complexity to compute a very large database of alias information. But the idea is once you've computed that database, then queries against the database to make alias queries are cheap. We have a problem with this in our current alias analysis framework right now in LLVM. We don't have any way for an alias analysis pass to keep state. In order to keep state, we have to have a strategy for how that state is going to keep current as the IR changes. And right now, our current pass manager is not capable of describing the needs of an alias analysis pass that keeps state. So that's one of the problems with Anderson's. The other problem is that this solving phase takes so much time. People have done research on Anderson's and alias analysis to try to understand, is there ways we can make it faster, make it more practical? And I understand that the people working on this in LLVM did a lot of the crazy offline cycle optimization kinds of things with Anderson's and weren't able to actually get the compile time down enough to be usable. So this pass has been removed from the tree. But having a stateful analysis is something that we're hoping to look at someday when we have a chance to make the pass manager infrastructure less inflexible. So with that, I'm going to move on to the TBAA portion of alias analysis, which is sort of the main subject of this talk. The basic idea of TBAA is if you have two pointers to different objects and the objects have different types, you can say that those pointers don't alias. In short, an int is not a float. So if you have a pointer to an int, it won't be pointing to a float in memory. This is a concept that's in the C89 language, and it's also in C99, and also in C++. And we call it type-based aliasing. Sometimes it's spelled TBAA, which we pronounce as TBAA, which comes from the Vulcan TBAA. Anyway, so TBAA and C, they actually had to adapt it in C99 and C++ because this concept of memory having a type is actually kind of a contentious topic in C. People do things like type punning. You take a region of memory and say, this region of memory has an int, but I want to access it like a float because I want to do sort of float things with it. But then later on, I'm going to want to access that same bit pattern as an int. It turns out that the C language is actually really difficult to express this concept in because of people doing these type hunting, and you want to make the type hunting legal, but you also want to have strong alias analysis because C is a language with lots of pointers, so there's this sort of conflict. And this leads us to the dark side of C, where you have, here's a piece of code which is perfectly innocent. This code breaks no rules in the C standard, where we have a pointer to int and we have a pointer to float. We use the pointer to int, we store to it and then load from it again. And then we use the pointer to float, we store to it and load from it again. And then I just have this here to make sure that the code doesn't all get deleted. As an optimizer, it may be the case that we might want to take this load and move it up above the store, above that integer store. And the question is that safe? With the basic type-based aliasing rules, that is safe, because a float is not an int. So the int pointer and the float pointer are pointing to different regions of memory, and we're safe, right? However, what happens if this x and y are pointing to different members of the same union? Now they really are pointing to the same memory. Even though we said that an int and a float were different things, we have this thing called a union, which means that you can actually put these things in the same memory. So it's not actually safe for the optimizer to do this. In fact, the optimizer has no way of knowing that there even could be a union here. That's sort of a mystery. There's no way we can know because we can't always rely on being able to see the entire program to know where the unions are. So it turns out that this is actually a fundamental problem with the C language in the C standard, and the C++ standard inherits this as well. And what it means for optimizer writers is that we have this kind of gray area territory that we have to interpret the standard and have to make our own decisions. We have no help from the standard. We have to make our own decision of how aggressive we want to be, how aggressive we want to try to interpret these rules and push the boundaries on punishing people for doing questionable things with pointers versus getting good optimization. It's an interesting trade-off that we all have to make ourselves. So C++ may not be quite as bad as C. C++, of course, inherits the same problem from C. But C++ also has virtual classes that have vtable pointers. And has a lot more rigorous rules about you can't just take a blob of bytes in memory and say, this thing is an object with a vtable pointer. In order to create a true object in C++, you actually have to call the constructor. In order for it to be deallocated, you actually have to call the destructor. So in C++, we may have a bit more of a sturdier foundation here, but it's not totally clear. This is actually sort of an ongoing subject of debate within the compiler community of exactly what we can do with C++ alias analysis. So as I mentioned before, memory in LLVM, in the LLVM's own type system, memory has no types. And we wanted the design of TBAA was that we wanted a system where we could really separate the mechanism of alias analysis, the actual optimizer pass that does that answers the query, from the business of interpreting what the C language actually means, which is actually a rather difficult thing. So we've separated mechanism and policy. We've put the burden of interpreting the C standard into the front end. And we have a system where the front end can decide what the standard means and encode a type system in a metadata system in LLVM. We're using the LLVM metadata so that the front end can actually cook up whatever kind of type system it wants, following a few simple rules. And then the optimizer has the simple job of just interpreting those rules and not having to worry about whether or not it's actually interpreting C or C++ or Ada or Fortran or any other language with its own rules correctly. Another big goal with the TBAA and LLVM is to use this chaining behavior we have of alias analysis passes in order to be conservative about type hunting. I'm going to actually have an example of that a little bit later. And we also want to support cross-language inlining. If you want to have some C code, you want to inline that into some Ada code or some Java code or whatever code you have, we want to be able to inline this code together into one LLVM bitcode file and have it all work. So the type-based aliasing design is designed to do this with this concept of type trees. The type system is described in a tree. And if we have two different languages, for example, I have a language called regular C and a language called crazy C. In regular C, we have a tree of types. And the way this tree works is that a type that's an ancestor of another type is a potential alias of another type. So in this case, float is an alias of char. And the regular C standard actually does say this, that the char type aliases all other types. But float is not an alias of int. And then I have another imaginary language over here where float is an alias of int. And by keeping these as separate trees, we have an additional rule that says if you do an alias query with types from different trees, that's always a mate-alias relationship. So if we don't know, we have to have, if we have two languages code from two languages being inlined and mixed together, we're actually able to sort of keep their type trees separate. It's two separate conceptual type trees. So we can actually be somewhat conservative at the boundary, which is exactly what we want to be for type-based aliasing, especially when you're mixing different languages that have different type-based aliasing semantics. So the tree system we have right now isn't completely sufficient for all the things we want to do. There are times when a particular memory reference might have multiple types involved with it. For example, if you have a struct, and this struct has an int and a float, if you have a store of this struct, that store could be overriding memory which has an int, or it could be overriding memory which has a float in the float part. So one way to represent this within our sort of type tree system would be to make it a type DAG and say, my class is now a descendant of both float and int. The alias query would still work in the same way. You still have this property of type as an alias if it's an ancestor, or it has an ancestor, or if the other type is an ancestor of it. But it would just be a little bit more work to make that query within a DAG, within a tree, but it would give us this more flexibility. This may be an extension we may add to the alias analysis in the future. Another interesting way we can extend this is we can actually add additional types to the tree. So if we say that if we add new types for each member of the class, we can actually say that this isn't just any, this class doesn't just reference any int. We actually have a member saying the int member of this class is a different type from the int member of another class. And this actually could give us a lot more precise alias analysis information for struct members. And this is another extension that we're considering adding in the future. So we might make the type tree a type DAG. We don't know actually for sure yet. Another way to do this would be to say an instruction can have multiple tags. Right now, a loader and store can only have one tag saying this is the type of this loader and store. But what if we had an instruction that could have multiple tags saying this instruction may be loading any one of these types? That would essentially be a way of keeping the tree structure we have right now instead of going to a DAG structure. We would still have, essentially have to do multiple queries, one for each tag, every time we look at that instruction. And then it's also possible we could add a new data structure. We would have a type tree describing the sort of scalar base types. We have a separate structure describing how types are aggregated together in various aggregate structures would be another way of doing that. Another quick slide on type planning. So this is an important issue. It's sort of at the heart of type-based alias analysis is this question of if someone writes code like this, if you have an int and we force it to be referenced as a float, and then we reference it as an int again. If you ask alias analysis, well, do these stores alias or not? The TBAA pass will say no alias because it's an int and a float, and those things are different. The basic AA pass says must alias, the exact opposite, because it can actually climb up the pointer chain and say these things are actually pointing to the same memory. So which one's right? The way we do this in LLVM is that we use our chaining. Basic A is always lined up first in the chain before TBAA. So we come to basic A, and it says must alias. And then we don't proceed on to ask TBAA what it thinks. We just stop and say, OK, that's a fine answer for me. And by using this approach, we're actually able to make type-based alias analysis conservative in the face of type planning. So basic A will try as hard as it can to find a must alias. It'll search up as far as it can go. It's sort of a best effort of try to find the type planning. If you try as hard as you can and you fail, then you're allowed to fall back and go back to type-based aliasing rules. And this rule seems to work pretty well in practice. It seems to, on large code bases, it seems to avoid a lot of the sort of classical problems that people have had with type-based alias analysis. Although, again, just today I learned that there are potentially code in the world that even this kind of a conservative approach does not work for. So we're going to be continuing to look at ways to make this more safe for real users to use in real field, and also still effective for optimization. So that's all the slides I have. Do we have any questions? Yes, Eli?
So if these come, these are 2 pointers that come from a function argument. So also, the basic analysis would not say must alias, but then TBAA could say, like, no alias because these are different pointer types. Mm-hmm. But that could be wrong.
That's right.
Why?
So that's because as I mentioned earlier, the way type-based aliasing is defined in C fundamentally has that problem. That's an open problem that's not solved by the standard. So we are attempting to make a trade-off where we can get a fair amount of optimization. We try as hard as we can to detect that problem, although sometimes we can't. So in practice, we try to be as safe as we can while still getting some benefit. That's essentially the trade-off that's being made here.
But you must be conservative in order to not generate their own code, right? Eventually, you can't say no alias for this case.
Something like this, where people are directly manipulating the bits of a floating point number or something like that. Like that's a very important case. It's if we actually broke this, it would really we're not really doing our duty to our users, right? But ultimately, as long as we get the really obvious cases, that it's more reasonable to say, we can go to users and say, okay, we're miscompiling your code, sure, but we're miscompiling it because it's invalid and because you're breaking the rules of C.
Okay. So it's kind of the undefined behavior kind of thing.
Yeah, although actually the degree to which their code is actually invalid is not a totally open and shut case, right? So that's an ambiguity that's in the standard, and we can't really do anything about that. So we basically offer the users a choice. You can say, you can use -f no strict aliasing, which is a command line option in Clang and GCC for that matter, to turn off this feature altogether. And if you do that, then we will be conservative in the way that maybe a lot of people expect us to be. But our default mode is to optimize more at the cost of potentially getting some corner cases like this wrong. Okay.
So just to follow up on that,
Oh, yeah,
sorry.
right, okay.
Just to follow up on that, I had the same concern. In this particular case, this code is undefined. And if it's undefined in C, then the compiler has the freedom to do what we're doing.
That's correct.
But are there any cases that are not undefined where you would have, where TBAA might introduce a bug like this?
Yeah, so I have my earlier example here. Oops. This example. So this code, I claim, breaks no rules in the C standard as written. Now, this doesn't show everything because we don't actually know where X and Y come from. If X and Y happen to be pointing to different memory locations, then everything is fine.
Right.
There are ways in C that they can be pointing to the same memory location. One of them is for them to be pointing to a union.
So
Another way is for them to be pointing at malloc memory, because malloc memory has no built-in concept of its own type. So this float store is actually sufficient to change the type of a malloc memory region in C, in some interpretations. So this would be an example of valid code that we would potentially break today.
So I think that was really my concern. It seems to me that we cannot be introducing analyses in LLVM that could potentially break code that is not undefined, that's actually well defined. And it seems to me that's a line that if we're going to cross, you have to be very careful about it, and I'm not sure that this is appropriate.
So I encourage you to take this up on a public mailing list or some other forum. This decision has been made. This is what we're doing. To do this optimization at all has been made. So in order to do this optimization at all, we need to break this code. I guess you were at the microphone first.
I might have missed it in your explanation. If we have a function and the parameter with no alias attribute, and then we inline this function, what happens with the parameter which is not a parameter anymore?
Right, so if you inline, you have a function with no alias on one of its parameters, and you inline the function, we essentially throw away the no alias keyword. That information is essentially lost. So that means we are more conservative in some situations than we would otherwise need to be. But again, the idea of basic AA being able to climb up pointer values to see how is it defined, in many cases, having no alias in the middle of a function is less important because that's a point where we can still keep climbing. It's at the boundary of an argument or we can't keep climbing past the end of an argument. That's where we really, really need it in most cases. Now, there are actually cases where having no alias in the middle of the function would be helpful. But we kind of have an 80-20 thing where we get 8% of the benefit on arguments for 20% of the effort. Supporting no alias in a local scope is actually a lot more complex, and there's a smaller benefit. So we're kind of at a sweet spot right now. All right, go ahead.
Yeah, back on this union thing. So in this example, you don't have a union inside the function. I wonder what happens if you declare a union inside the function and have two memory accesses to fields with different names, different types, following each other. What TBAA says in this case?
Right. So one thing I do want to mention, if you are a programmer and you want to do type hunting, unions are the way to do it. We love unions. We don't like doing type hunting with raw pointers. Unions are the best way to do it. Having said that, what will this look like? The references to the integer member of a union will have the integer tag on it. The references to the floating point member of the union will have the floating point member tag on it. TBAA would say no alias if you asked it. Even though that you use a union type in C, our TBAA pass would still say no alias because it's just looking at the actual type of the dereference, which is actually just the scalar type. In order to get this case right, we actually rely on this training behavior where we have to rely on basic AA coming in before TBAA and realizing that, oh, these pointers are actually coming from the same storage. This is actually a must alias situation. And potentially it's, in the case of a union, maybe with a union with struct members, it could also come back. This is where actually, I don't know if I mentioned this, but this is actually where we use the partial alias keyword, is basic AA can say, I'm pretty sure there's an overlap in some situations here, but I can't always tell. And I don't want to let go and have TBAA come in and say no alias because there's a good enough chance there might be an alias here. So we actually use partial alias analysis, partial alias as a result to sort of say, okay, stop, don't go and ask TBAA because it's going to give you the wrong answer. So that's essentially how we handle unions, is we rely on the basic AA to get it right.
Okay, so we have one follow-up.
Sorry, just a quick follow-up. So if I remember right, I think the case you're talking about is actually undefined in C. It is not legal to store a value into a union as one type and then load it out as a different type. And
so the degree
right?
to which type hunting is permitted in C is kind of a weird question. I think the people who wrote the C standard didn't agree amongst themselves, and when you read the standard, there's some conflicting language. Different parts seem to say that you can, and some parts seem to say that you can't. I think in practice, telling people that they can't type hunt is too restrictive. Like users in the real world actually do type hunting, so this is something that we have to deal with.
Right. You're talking about what users actually do as opposed to what the language standard says. The language standard says, I think it's reasonably precise about this, and the question comes down to what extent are you willing to break programs that don't obey the standard? And I think that's what it comes down to.
Yeah, and I also want to point out that I crafted this test case very carefully to actually even sidestep that issue. So here we're storing and loading in an int, and the first thing we do with the float is we store as a float and we load as a float. So this store, assuming this memory is like malloc memory that doesn't have any kind of built-in effective type, this store would actually change the effective type of the memory. So in this test case, even if these things are pointing to malloc memory, this test case ought to be valid. And the optimizer, following the type aliasing rules, will break it. So here we are breaking a completely defensible, valid piece of code. Okay. So this is an example. I'm bringing it up, and I'm telling you this because it's invalid, and we know it's invalid. I mean, it's a case where we miscompile, and we know we miscompile. And we're doing this as sort of a known trade-off. We're doing this because we think it's rare, and we think the optimization is worth it. Okay. I have to say that's not my own personal opinion necessarily. This has been the decision that's been made. We're going to do this optimization, and this code is going to be a victim, and that's just how we're going to do it.
Okay. So maybe just one last short question.
Okay. In the example of slide 1, AI equal to AI minus 1. So
yes.
Alias analysis say these two memory access not overlap, the load will be moved out of the loop. If the alias analysis say, well, they do alias, they will, disable some optimization in the intra-loop, like scalar optimization. So how does the interface give the right answer at the right moment?
So if you ask the alias analysis interface, does p sub I and p sub I minus 1 alias, it'll say no, because that interface is only set up to think about within one loop iteration at a time. If you go and ask the dependence analysis interface, it'll say you have a dependence at distance 1.
So I have
the decision is made by which pass you ask. If you ask alias analysis, you'll get an alias analysis answer. If you ask dependence analysis, you'll get a dependence analysis answer.
Okay, thank you.
Okay, yeah, great. Everyone for attending. Thanks a lot. And thanks a lot, Dan, for speaking.